We just showed that the pth power of e to the x is e to the px. The creature e to the x exhibits a multiplication rule for powers. We now show that the creature e to the x also exhibits an addition rule, namely e to the x times e to the y equals e to the x plus y. If you're tired, this might not be the best day for this. This module is really dense. The product e to the x times e to the y is represented by the product of the sum from k equals 0 to infinity of x to the k over k factorial, all of that multiplied against the sum from j equals 0 to infinity of y to the j over j factorial, or more explicitly all of this stuff. I am not reading all of that aloud. This product can be written as a double sum, the sum from k equals 0 to infinity of the sum from j equals 0 to infinity of x to the k, y to the j over k factorial, j factorial. This is interpreted as the sum of terms that look like x to the k, y to the j over k factorial, j factorial for every non-negative integer value of k and every non-negative integer value of j. This lattice displays the values that k and j can take. I'm going to walk quickly through a few terms to argue that the double sum is the product of the series expansions for e to the x and e to the y. But if you have never seen this before, you will probably need to pause and review this part of the video very slowly a few times. As our first example term, start with k equals 0, j equals 0. The term is x to the 0, y to the 0 over 0 factorial, 0 factorial. Move to the right, keeping k equals 0 and now having j equals 1. The term is x to the 0, y to the 1 over 0 factorial, 1 factorial. Analogous terms are obtained by continuing to move even further to the right. The position k equals 1, j equals 0 corresponds to the term x to the 1, y 0 over 1 factorial, 0 factorial. The neighboring lattice side to the right, k equals 1, j equals 1, corresponds to the term x to the 1, y to the 1 over 1 factorial, 1 factorial, and additional terms come from moving even farther to the right. The rest of the sum corresponds to additional rows above. The example terms that we have listed are the kinds of terms we expect to result from distributively multiplying the power series for e to the x against the power series for e to the y. Every point on the lattice, every combination of an integer value for k and an integer value for j, corresponds to one pair of turquoise and yellow terms multiplied together when the blue and orange power series are multiplied together. Another sequence in which we can place magenta dots to add up the pieces in the double sum starts with the same first term, k equals 0, j equals 0, then moves up to the lattice side k equals 1, j equals 0, descends diagonally to the right to the lattice side k equals 0, j equals 1, jumps back up to k equals 2, j equals 0, descends diagonally down toward the right to k equals 1, j equals 1, before hitting k equals 0, j equals 2. The rest of the lattice is accessed by repeating this diagonal motion. Each of these diagonals corresponds to a constant value of j plus k. For example, this diagonal corresponds to the constant value j plus k equals 0. These dots and these terms correspond to j plus k equals 1. These dots correspond to j plus k equals 2, and these other diagonals correspond to increasing integer values of j plus k. We can organize an equivalent double sum that explores all the pink dashed diagonals. That's the sum from j plus k equals 0 to infinity, and for each of those dashed pink lines, explores diagonally from left down toward the right. That's the sum from j equals 0 to j plus k. Relabel j plus k simply as L. Then k equals L minus j. Everywhere we had k, now substitute L minus j, and everywhere we had j plus k, now substitute L. We obtain the sum from L equals 0 to infinity of the sum from j equals 0 to L of x to the L minus j, y to the j, over L minus j factorial, j factorial. Open up some white space into which we can insert compensating factors of L factorial upstairs and downstairs. Move the powers of x and y off of the fraction bar and move the L factorial onto the fraction bar. Now we have a coefficient familiar from combinatorics, a first term, and a second term. We recognize the result of the binomial theorem. Put the mark for the first term on stage here, the mark for the second term goes here, and take both of these terms to some power, here. E to the x times e to the y equals the sum from L equals 0 to infinity of 1 over L factorial times the Lth power of x plus y. And formatting the sum nicely, we recognize e to the x plus y. We just showed that e to the x exhibits an addition rule you might have seen previously associated with exponentials in pre-algebra. Next, we will show that the value of e is 2.7 and some change.